Because you know, right? One of our students in our class got COVID yesterday. Is anyone in your college? Is it the college informed any close contact? No. Okay, one student from the class.
Our class.
Yeah. So.
I mean, that's the reason why I got down.
He said he's not feeling well.
So be safe, so keep distance. Yeah, so let's take attendance first. Yeah, so let's discuss for the first 20 minutes, maybe discussing about the E5, and we go ahead with discussing the theory. Okay, very good. Okay, do you try this the complete design of the stationary wave? You wrote the report, you check the bug scheme. $15. So how do you find the find the vibration mode? These are an experiment to investigate the resonant frequency for fundamental mode with tension. Okay. Of course, independent is the resonant frequency. Dependent is the tension. Variable to keep constant is what? The length of the string. The length of the string. We already discussed this the last week, right? It's just the beginning part. What is independent, what is dependent variable to keep constant. So how do you measure the resonance frequency? What instrument you use? Use the read from the signal generator. Signal generator, you can find the frequency. How do you measure the tension? By using the slotted mass at the side. Okay. Yeah, that's the two main things. Okay, so roughly should be like this, right? The setup. So independent tension, frequency of the signal generator, length of the wire. Okay. So under procedure, how many marks? How many marks for procedure? 4 marks, 1 for the diagram, another 3 for the procedure. So what do you need to write in the procedure? Right, how do you measure the frequency? How do you measure the tension? Okay, how do you keep the length constant? Okay, that should be in your procedure. So measure the weight by using a top end balance. Good mark. There, what instrument? Measure the tension. Measure the weight by using a top end balance. The tension is the weight of the solid mass. Okay. Measure the frequency until the fundamental mode is observed. One loop. One loop is fundamental, right? Okay, your AS knowledge. One loop formed. Adjust the frequency of the signal generator until one loop is formed. Until the fundamental mode of vibration is observed, the largest amplitude of oscillation is seen. So measure the frequency of the signal generator. 1 mark. 1 mark, main point. Measure the weight by using top end balance. 1 mark. Yeah, then repeat the experiment with varying different masses, but maintaining a constant length. Maintaining a constant length, mark of the wire. The largest amplitude observed could be a detail mark. To explain how to see the fundamental mode. Fundamental mode is consists of one loop with a large amplitude. Okay, so focus for procedure, always tell how to measure dependent what instrument, dependent what instrument, how to variable to cap constant, what to cap constant. Okay, analysis, of course, there's no answer here, because no equation given, but I give you the equation, right? What equation I told you to adapt that day? The frequency is E equals to F lambda. The F is proportional to root of tension, right? dq. Frequency is proportional to root of tension. Okay, I think that's the equation I asked you. The proportionality I asked you to include. Or you can put frequency equals to k root of t. F equals to k root of t. Okay. So based on that equation, what is the analysis going to be? So plot what versus what? F equals to k root of t. K is constant. So what graph is to be plotted? Plot F versus root t. Normally root t is not preferred. You square both sides. So what graph is the best? Plot F squared versus t. Right? Plot F squared versus t. Okay. Or you can see F versus root t accepted, but normally root t not good. Normally we square both sides. So plot F squared versus t. Okay, 1 mark. Then what else you see? Yeah, analysis by obtaining a straight line pass through origin, right? By obtaining a straight line pass through origin, where the gradient represents what? The gradient represents k. Okay, would enable us to validate the relation. Okay. By obtaining a straight line pass through origin, where the k as the gradient of the graph would enable us to validate the relation. Oh yeah, sorry, k square. Yeah, k square. This is k square, right? Thanks. by obtaining a straight line pass through origin where the gradient is equal to the k square, would enable us to validate the relation. That should be under analysis. Okay, precaution, whenever you got string, might snap, might hit your eyes or something, so use goggles, like goggles. Got sorted mass and back to be used, bucket of sand, okay? Then the mass fall into the bucket of sand, not just fall on the floor and might hurt you. Whenever there is string, goggles. Whenever there is a sorted mass, bucket of sand. Okay. Whenever there is current, use gloves and handle the circuit. Okay. Whenever there is something hot, again gloves. Okay. I think there is a list of safety, right, in the document. Design experiment at the back. Whenever involving radioactive experiment, what is the safety? Radioactive experiment. What is the safety you use? Use tongs to handle the what do you call the radioactive substance. Okay. Wash your hand after conduct the experiment. Okay. I think radioactivity got a lot of safety. Use tongs, a long plier to hold and put it somewhere the radioactive substance. Lead coated screen maybe. Okay. If you use laser, what is the safety? If you use laser,
I wear shades.
okay. So don't look directly to the laser. Yeah. Okay, so that's box safety, 1 mark for it. Okay, then of course this is where you need to get how many details? 6. You must get at least 6 details, including the safety one. 5 details. So yeah, in this case, first one is good. White cut. Use a white cut at the back of the vibration so that it can be seen easily. Okay. So that we can observe that the single loop already formed by placing a white cut board at the back. So easy for us to observe the oscillation. Okay, determine the preliminary experiment, determine the suitable loads to be used. If it's too heavy, then the tension going to be high, so the frequency going to be higher. Okay, maybe exceeds the frequency available in the single generator. Okay, so we don't want to have a very high load and a very low load, intermediate. So you find the preliminary experiment so that the frequency is within the range of the signal generator. Okay, you don't want out of the frequency of the signal generator. You can't form the signal. So conduct a preliminary experiment so that suitable load is used. So make sure the wire is free from kinks, so uniform cross section, so the tension is same throughout. Use micrometer gauge to check the wire uniformity. So it's free from kinks. So kinks means some part is the cross section area is too small, so tension is not uniform. Now, whenever you use pulley, make sure pulley is smooth, frictionless pulley. Okay, any other extra detail? Always you can write this, but don't know whether they accept or not. Okay, the repetition. Okay, repeat the experiment, obtain the average. Always include that. Okay, repeat the readings for the frequency and obtain the average. Parallax error here, not necessary to have a parallax error. Just see the repetition maybe. Repetition very common. But always include. It's okay. Okay, when you write, always diagram, subtitle, the first subtitle should be for the method. On top of method, independent, dependent, variable to control. Then subtitle, method, so in point form, then analysis, subtitle, then point form, and straight go for extra detail. Safety put under extra detail. You got to put it separately also can. Safety first and extra detail. Okay, so now we go to another design. Not we're going to do completely again, just set up only, draw. Okay, just draw for 10 minutes. 10 minutes, get the drawing. What do you think? What instrument needed? So we go for maybe radiation of magnet. Okay, different type. Okay, go back to the. Okay, so we skip after D5. Check D6 is just telecommunication. Okay, go for one radiation. Can expand. It's usually learn nuclear. Okay, okay, come on, have a look. 10 minutes for you. Try to get the design, what instrument to use, how you will go about for this. Okay. We show first 10 minutes to get the design. How you will design an experiment to prove that. We want you to investigate how the range of the alpha particle is related to P like this. Prove this equation is correct. Okay. So first thing, always you need to identify what is independent, what is dependent, what is variable to get constant. That's the fundamental. And only you can start to design. So write first what is independent, what is dependent, what is variable to get constant. Get what is independent, dependent variable to kept constant. That's wrong. Your experiment setup went wrong. What's independent? Range, right? Range is independent. What is dependent? Yes, sorry. What is independent? Dependent is your pressure, right? Pressure is independent. You change the pressure, right? Pressure is independent. What is dependent? Range is dependent. We adjust the pressure, we check the range, how far the alpha travels. So independent is of course pressure, right? Dependent is the range. What is the variable to keep constant? Yeah, anybody? Give a try from your mind. What is the variable to keep constant?
Volume of the
Temperature. Temperature affects radioactivity? No. The type of radioactive substance?
maybe
Yeah.
it does.
Okay.
I think it does.
The mass.
The temperature of things.
Temperature, I don't think so. Because temperature never affects radioactivity. Okay. So maybe the quantity, the mass of the radioactive substance. The mass of the radioactive substance is always the same. Of course, right? Greater the mass means you use different mass means the activity changes. Activity is proportional to number of particles, right? The first formula, A equals to lambda. So the mass of the radioactive substance, right? You get constant.
How about volume of air?
Volume of air. If you use different volume, yeah, good. The density of the air. The density of the air also kept constant. Greater the density, I think range might be affected, right? Alpha cannot travel too dense, so even short range. The density of air also kept constant. The density of the air is kept constant. Close contained. Good. So that's independent, dependent. Independent definitely pressure, dependent definitely range, and kept constant the amount of the radioactive substance, the density of the air. We now draw one diagram. Come on.
This is
the hardest one.
alpha particle.
Yeah.
And let's say alpha particle electrons.
The substance is alpha particle. Kept constant.
I mean, in the diagram.
Oh, you just want to put as alpha. So how the setup going to look like? How are you going to vary the pressure? What instrument do you use to vary the pressure? Okay, how are you going to measure the radioactivity? What instrument do you use to measure the radioactivity? Okay. How do you measure how do you change pressure? First time you involve with pressure. Do you need any setup before pressure? How do you change pressure of a container? Use what? Vacuum pump. Use a vacuum pump. Connected to a vacuum pump. Okay. Remove the air. Vacuum pump is a pump that it's a pump that removes the air from the container. Okay. So when you remove the air, the pressure change. So vacuum pump. How do you measure to change the pressure? You use vacuum pump. But to measure the pressure, what instrument do you use? What instrument to use to measure pressure? Barometer is it to measure what pressure? Atmospheric pressure, right? So for gas pressure, we use manometer. Bottom gauge, right? Bottom gauge of manometer is used. Okay. How do you measure the radioactivity? Just recently you learned on the nuclear topic, right? How to measure radioactivity? GMQ connected to a rate meter. GM, gigamolar chip connected to a rate meter. Okay, GM chip connected to a rate meter. Okay, so trying to have some setup. I know I'm going to show you one, and but you draw yours. So, from that one, just do it. Remember, in your mind, you must know about background radiation. Yeah? Must do something to do with the background radiation. Background radiation, I think, will be under Xray detail. Okay, so let me show you D9, right? Hopefully the setup roughly like this. So vacuum pump, boron gauge or pressure gauge, okay, manometer, lead box. And of course, the radiating substance need to be in a lead box, right? The MTM connected to a rate meter, put on and pull it, because you pull it until to find the range. But how do you know you already reached the range? How do you know you reached the range? When do you stop calculating? When do you think as that distance as the range? The reading dropped to what? The reading dropped to the background radiation, right? So before you conduct the experiment, first you have to find the background radiation. Background radiation, let's say, keep a count rate of 2000. When you put closer here, maybe the reading is 5000. 2000 by the background, 3000 by this radioactive source, let's say. So you have to move it until the radiation for the first time dropped to 2000 to the background radiation. When it comes to the background radiation means conclusion, the radiation of that substance, the radiated substance doesn't reach that point. That's the range. Yeah? This is okay, let's say it's safety here. Strong glass container needed, right? Pressure you are changing inside. The pressure inside decreases means pressure outside greater, there is a chance to collapse, right? Okay, it can break. Okay, pressure difference causes a net force, they can break the glass. Any experiment involving pressure change, the container have to be a container can withstand a high pressure. Okay. Before you conduct this experiment, get the reading without the radioactive source. Get the background radiation. That's extra detail. Then have the lead box, the radioactive source.
So you pull the But you have to until it's just background radiation.
Until it dropped for the first time to a background radiation. Yeah. So move the trolley until the watch monitor the reading of the read meter. Okay. Check the distance where for the first time the reading dropped to the background radiation. That distance is the range, that particular range. Okay, so this is your homework again. Okay, the method, the analysis part, all try to write first. Okay, and of course I insist on the time, so don't look at it. So you write yours, and as a reference, go and check. Okay, so you need to get how many marks? 15 out of. So you need to score at least 10, quite sufficient to score to get A. First question out of 15, you should score 13 or 14. So this you get 10 also already 24, 24 is already A. You need to get at least 23 out of 30 to get A. But more is good, of course. More score is good. Yeah.
Is the last box inside the glass?
That box have to be inside the glass. Why? It should not. It cannot be outside. If it's outside, the glass going to block it, so the range will be affected, right? So we don't want the alpha to be blocked by anything. So you have to be inside. And the LED box normally, they here show LED box, but normally it will be like this. Okay, the LED box, the LED box you can draw like this. Okay, the LED box you can draw like this. You can draw like this. You have the radioactive substance. So that this is the radioactive substance. Okay, radioactive substance. This is the LED box. LED box. So that the radiation only comes out in one direction. Okay, we don't want it to come out in all directions. Okay, so LED box. Okay. Have to be inside. If it's outside, then the glass will block the alpha radiation, right? Range effect. So have to be inside. Because you know alpha, even a piece of paper can block it. Okay, class. So homework. So we go back to the theory. Your topic 14. Okay, we try to finish the ultrasound. Okay. Okay, the C6 part 6, go to the past year papers, do more part C. I mean the analysis questions. Okay, so let's go back to ultrasound. Okay, so we almost done with the ultrasound, around 70%. Just fact. Okay. Now today, as we're going to go for the calculation, I think last class, just towards the end, I introduced the calculation for ultrasound. Okay, they will ask what is the ratio of the intensity of the receiving intensity and to the original intensity. Okay, so these are the earlier one, right? Okay, so recall back from the calculation, partially reflected, partially transmitted, and the intensity I reflected plus transmitted should be the total intensity. Then a new quantity was introduced, recall back, something called acoustic impedance. Acoustic impedance is what? It's the product of the density of the medium and the speed of the sound, that medium. Acoustic impedance. Why acoustic impedance so important? Because acoustic impedance determines the how much intensity will be reflected. Okay? So the coefficient of reflection is dependent to what is called the acoustic impedance of the both medium. So I over I is your alpha. Okay. Then these values all will be given. Then we found that something travel from air to soft tissue, 99 reflected. Okay. And muscle to bone, 34% is reflected. Okay, so gel is used to make majority transmit. So the gel must have the same acoustic impedance as the skin. Then we say something called absorption happens. Halfway, it's never contribute to the imaging. Yeah. So therefore, the absorption depends on how thick is the material, the tissue, and the K value. K is called absorption coefficient. Dependent to two factors. Of course, only one factor here. It's dependent to the frequency of the ultrasound send. Higher the frequency of the ultrasound, more greater the K. That means greater the K means what? The depth is you can go deep or unable to go deep. Can't go deep. High frequency ultrasound difficult to go deeper into the body because absorption coefficient is very high. Very absorbable. Okay? High frequency. And depend on the nature of tissue also. Bone absorption. Okay, yeah, so this is the question we went to the whiteboard and I explained to you. Okay, now try to understand the concept. So here, a parallel beam. Okay, the question. We done this because the last part is the fraction of the receive, the intensity of the receive over the original intensity. Not be one of you. Maybe I show you this with my example. But here is part by part. Ready the question? Try to imagine how the intensity moves. A parallel beam of ultrasound incident on the surface of a muscle and passes through a thickness of 3.5 centimeter of muscle. So there is a muscle which is about 3.5, okay, muscle is then reflected at the surface of a bone. So next layer is bone. So this is bone and returns through the muscle to its surface. So so this is the original intensity I naught goes from the muscle, reach the bone, and reflect back to the muscle again. This is your okay. So I just put I. Okay. So that's the diagram, right? So 3.5 centimeter thickness of muscle. The original intensity gets into the muscle, and muscle and bone layer after travel 3.5 centimeter, it was reflected and reached the muscle surface again. Okay. 3.5 muscle is then reflected at the surface of the bone and returns through the muscle to its surface. The diagram. Using the data from the table above, okay, and the earlier tables too. Calculate the fraction of incident intensity that arrives at the surface of the muscle. So how many fraction of incident intensity reach the surface of the muscle? So question asking for what? I over I naught, how much? I over I naught. So I over I naught, how do you define? You get this 1 over 50. Use the method I told you. How many times absorbed? How many times reflected? Twice absorbed. Every time absorbed, what formula you must use? E equals to negative kx, okay, for absorption. So the original intensity, the final intensity is I, we put here, equals to I naught. At the side here, you need to include, you have to include, multiply by the absorption, reflection, and everything. So I equals to, already out. Okay, I equals to I naught. Okay, what do you write then? How many times absorb? So twice absorb, right? So E negative multiplied by E negative kx multiplied by E negative kx twice. So actually E negative 2kx, okay? 2 times absorption, right? So multiply by what? So here need to be multiplied by E negative 2kx lah, twice absorption. Twice absorption. Then multiply by 1 time reflected, right? Reflect go up. So reflection multiply by what? Multiply by the alpha. Reflection is alpha, right? So multiply by alpha. Alpha of which medium? Alpha of the muscle bone, muscle and bone alpha. That's all. Okay. This is the conclusion, right? Okay, now check. You get 1 over 50. E. So I not bring to the other side. It's I over I naught. That's the fractional we want. So I over I naught is E negative 2kx times alpha. You get 1 over 50. E negative 2kx. How much? So here it's part by part. E negative kx. E negative kx. Negative 2.3. 0.23 is your. This is what? Muscle, right? Muscle absorption coefficient for muscle is 23 per meter. Here given 0.23. Why? Of course, again, I forgot to tell you this time. Both must have same unit. If the K is if the thickness is in meter, means the K have to be per meter. Okay. So like your half-life, lambda and T must be the same unit, right? Time is in second, means lambda must be per second. Time in year means lambda must be per year. The same concept here. So negative 0.23 in centimeter, right? 23 per meter means in centimeter per meter divided by 100, 0.23. Negative 0.23. Times 7, did you agree 7? Because they did negative 2kx, 2 times x, 7, 2 times of the 3.5, 3.5, 7. So this is the 0.2 is the value of E negative 2kx. Okay. The 0.2kx is your 0.2. 0.2. Alpha is how much? Alpha is alpha the previous slide values. Alpha of what you need to know? Muscle and bone. Muscle and bone alpha we calculated earlier slides. The alpha is found to be 0.34. Okay. Muscle and bone you got 0.34, right? Alright. Muscle and bone, 0.34. This is alpha for muscle and bone. Okay. So alpha 0.34, so here alpha is 0.34. So here 0.34. This is I naught, this is I. So I over I naught will be what? 0.2 times 0.34. You get 1 over 15. 0.2 times 0.34. You got I of 0.34, 0.06. So the fraction reached the surface of the muscle is only about 6.8% of the original intent. Reached the surface. Yeah, 6.8%.
Well, you get a mistake.
Yeah.
Really,
Oh, acoustic impedance. The previous slide. In exam, alpha they must give the table 4. Okay. Must give the acoustic impedance. Okay, this is the common one. Just one layer of reflection. That day I showed you 2 layers. So far never happened 2 layers, only 1 layer. 1 layer, the last. So you check how many times absorb, how many times reflect, get that. Okay. Okay, we'll be doing more questions like this towards the end. But this is the typical one, only one by ultrasound. Okay, again, facts. Significance of absorption. Okay, got one problem. When ultrasound used, the ultrasound is absorbed into the tissue. So when the energy is absorbed into the tissue heats up. Okay. So absorbed energy has to remain within the limit that does not heat the tissue to dangerous temperature. So you can't prolong use ultrasound to heat the tissue, and damage the tissue. Okay. And of course, this absorption acts as a limiting factor to go deep. Okay. If a lot absorbed means the ultrasound cannot go deep. Okay, to do investigation. Okay, like bone. Okay, first layer itself is a bone means all going to be absorbed, so the ultrasound can't go deep. Okay, and even reflection also going to be very small. Yeah, so this is the two problem of absorption. Dangerous to the tissue because it absorbs energy, heats up the tissue. Second problem, it affects the depth the ultrasound goes. Okay. There is one side benefit. The physiotherapy use ultrasound to give a slight heating to the joint tissues. Okay, can speed up the sprain joints. Any problem with the sprain joint, recovery from the sprain joints. Okay, a slight heat to the joints can improve fasten the recovery. Used by physiotherapy. It's a side benefit. But remember, there are two problems for high absorption. Can't go deep, ultrasound. Another one is heat energy absorbed by the tissue can damage the tissue. Okay. Limited energy absorption is good. Okay, used by the physiotherapy. Okay. Okay, I already highlighted this. The factor affecting absorption. Two factors: the density of the tissue, the type of tissue. More denser the tissue, more greater the absorption. Bone, okay, of course. So fluid, bone, calcification, bone absorb the most ultrasound. And second is the depends on the frequency of the ultrasound. Higher the frequency of the ultrasound, more absorption. Okay. So this. The desired depth to the image set the limit for how high frequency they can be used. You can see the criteria might be increasing the transfer. Okay. And the doctor want to use, okay, when do you will use for high frequency, when do you will use a low frequency? What is the benefit of using high frequency? High frequency means better resolution. Okay, better resolution. The kidney stone with a small size can be detected by using an ultrasound with a high frequency. Okay, so go to the my God. Okay, let's say body you have the kidney. Okay, in the kidney you have a stone, small stone here. Okay, so you send a ultrasound. The ultrasound, if it has a low frequency, means big wavelength, so it will travel like this. Okay, so you might miss the stone. Okay, but if it's a high frequency, means high frequency, the wavelength is short, so it will be like this. Okay, better searching. So you might detect high chance to detect the small stone. Okay, so better searching for high frequency. But problem is what? cannot go deep. Okay? So high frequency, good, better resolution, but cannot go deep. Okay? If you want to, the doctor want to see a deep section, no choice. You have to compromise with the resolution. You have to go for low frequency, go deep, but resolution not that good. Okay? So normally, if you want to put ultrasound, check the kidney, they put back, so they get quite close. Okay? Okay, so this the design tabs to be imaged, set the limit for how the high frequency that can be used. So you want to, it's quite less depth, can use high frequency. As can digit penetration by the increasing the transmitted energy, but this will increase the total absorbed energy, which has to stay below the safety limit. That is, a lower frequency is used for deeper penetration, 3.5 megahertz, and higher frequency, 7.5 megahertz, used for the superficial area. High frequencies will give an image of. High frequency will give a better resolution. More smaller abnormality can be detected. Yeah, high frequency. So all the doctors, of course, not all. Some doctors good in ultrasound. They have to go for training, of course. So they how to adjust the frequencies, how to see the image. Sometimes most hospitals only the technicians. Technicians will be using. They are quite good, because they use in the many times they doing the scanning. So compared to doctors, sometimes I think technicians know better the image. Yeah. Yeah. So from this image, you should know the dark region means what happened. A lot ultrasound has been absorbed. Okay. Nothing reflected. Okay. A lot reflected, it shows a white. White means a lot reflected. Okay. This a lot has been absorbed. Okay. So bone will be dark. Bone will be very dark. If your stomach got a lot of gas, and they put the ultrasound, what you will be seeing? Completely white. All reflected. Okay. I would go in depth. Yeah. Okay. So just a few slides. This is the last part. The ultrasound got two types of staging. Got A scan, B scan. Okay. What is A scan? A scan just send the ultrasound. You only get the what you call. This is 2D. Sorry, 1D. You just tell the depth. How deep is the next layer? Okay. How deep is the next layer? Maybe the first layer is the retina here. The next layer. Okay. And electrode, next layer. So A scan used to measure the distance, I mean the time taken for the pulse to rebound, come back, in order to determine how far away the boundary is. Okay. A scan only gives one-dimensional information, how far away the boundary. Okay. Soft tissue to the bone layer, how far away from the surface. Okay. That's all. But how the shape can't monitor. Okay. One-dimensional information, therefore not useful for imaging. One D is fine. How deep is the layer? So that's A scan. Okay. A scan, one-dimensional image. What you get from that one-dimensional image? The depth of the boundary. Only you get to know the depth of the boundary. Okay, A scan. So this is the skull. So the transmitted pulse, the skull reflected. Okay. You got inner region. A scan system measures the distance to different boundaries of the transmitter. The transmitter held in one position, some bursts of ultrasound transmitted to the body. Each boundary, some ultrasound reflected, some transmitted. As a fast feedback, amplified and displayed. How deep is it depends on the time, what do you call the time interval to the transmission. More longer, more deeper the layer, right? Okay, some energy loss due to absorption as usual. Yeah. So it's a scan 1D. Okay, now we never use A scan. We go for the other one, B scan. B scan and now getting more advanced. B scan is a series of A scan combined forms the B scan. Okay. They put the transducer here, A scan, and they move around the transducer. Few A scan is captured. The images will be combined to form a layer. Shows the layer. Okay. So B scan can be used to take the image of a cross section through the body. The transducer is swept across the area, move around. And the time taken for path to return is used to determine the distance. It's plotted as a series of dots on the image. B scan will give two-dimensional information about the cross section. It's a 2D view. A scan 1D is 2D view. You can see the layer of the boundary. Okay. So the boundary have to be straight, but here got a little culture, so they say some sort of growth. Then you have to go for further scanning. MRI or CT scan, okay. Maybe do some biopsy to check if the cancer tissue or one. Okay. So further testing will be done. This is the primary testing. Ultrasound and Xray is the primary testing. If anything abnormality shown, go to the next level. MRI, CT scan. Very serious, go for biopsy. Okay. Okay, yeah, no, I told you that. So the series of image A scan is combined to form a B scan. B scan technique combines a series of A scan taken from a range of different angles to form a two-dimensional picture. Showing slightly different orientation, bright spot, screen of CRO. This fine. The first table is now. In exam, they'll ask the difference between A scan and B scan. Okay, so A scan 1D, B scan is 2D. Okay. A scan only tells the depth, B scan tells the outline, the layer of the boundary. Okay. B scan is actually a series of A scan combined. Okay, forms a B scan. Here we got 3D, 4D already from that. 3D uses the same principle of 2D ultrasound, but the sound wave emitted from all angles of that. Show a 3D image. Okay. So 4D, 3D plus the movement. 4D, time function is integrated. So 4D ultrasound uses 3D technology but added a time dimension. So the picture is run frame by frame to show the movement. This is a movement, it's heart. Okay. Heart. How the, what is the one name? What? Take biology. You're training about heart. A-level. You want to plant or want to human? A-level. Both. So, learn about human body, heart. Long time ago, 11. So yeah, what is the what name? What? Then microscope. This is that. So yeah, the doctor, newborn about 6 or 7 months old baby, let's say in the womb, they will check how the heart functions, how the brain grows, everything. Okay. Heart function they can check by using the ultrasound, check how the valve workings and everything. So everything can be detected using ultrasound for the babies, for the small. And of course, your heart. Let's say you suspect you got a heart block. Okay. When you go to the hospital, the first test they're going to do is echo by using ultrasound. Okay. They send ultrasound to the heart. They check how the heart muscles are working. Okay. The movement of the heart muscles. Okay. If there is a block, you see the heart muscle movement is slightly a different rhythm. Okay. So that's the first level of testing by using ultrasound echo. Then if they're not happy, they'll ask you to go for a stress echo. Stress echo means what? They fix all the wires ask you to run on a treadmill. Okay? So let your heart rate goes up, connected to a ECG. Second one. That's the second line. If you suspect you can't go for the fourth level of running, then go for what? Angio. Check. Get into the small, small kind of needle, right? Get into your body. Check if there any block. Okay. So finally, you have to know what is the advantage and disadvantage of ultrasound. So advantage, image, you can take image of soft tissues, no bone, so that's the disadvantage. Differently colored in the soil and fluid. Okay. Another good news is instant image. Immediately you can see. Yeah, it's an instant image. Not like X-ray. After you take image, you have to wait for a while. Okay. CT scan also you have to wait for a while. MRI also need time to process. This fast, this instant image advantage. Yeah, you can check how the organs are working. Another important advantage compared to other techniques, of course, no known side effect. Okay, that's why there is no known side effects so far. Okay, not very harmful. Another advantage, the machine itself is relatively small. When we carry it into the ambulance, okay, ultrasound. Not like MRI, not portable. X-ray, not portable. Dangerous. CT scan also not portable. This one is portable. I can carry it to the ambulance. So this is all advantage. Ultrasound. Okay, so what is the disadvantage? Cannot detect bone. Not very good resolution compared to MRI and CT scan. Yeah, the weakness of ultrasound. Bone, big problem. Cannot penetrate bone. So any problem, you fall down, you've got problem in the bone, go for X-ray. Get some radiation, so your cells are affected. This one can do, all go for ultrasound. X-ray will become obsolete. Still need X-ray because of ultrasound cannot penetrate bone. Okay, as I said, got gas, majority will be reflected, so cannot examine the target organ underneath the gas layer. Cannot penetrate deep into the body to make the diagnostic organ that are deep in the body. They're very difficult because can't go very deep. So over 18 constants, that's how we discussed, can damage the tissue. Okay. Rise temperature may cause the formation of bubble cavitation. So cavitation in the tissue. Okay. But overall, ultrasound is safe. Not safe. Not really. You go to the excessive heat. Excessive heat means you prolong using the ultrasound for a long period. Okay. The main disadvantage, of course, cannot check bone and cannot go deep. That's all about ultrasound. Okay. I think it's a long story, just now I told you, but remember, you can come out like a 6 months question, explain the principle behind the use of ultrasound. Actually, you need to memorize this. This is the 6 points you have to memorize. Okay, memorize the hard. Okay. Some of the principle on the ultrasound, the principle behind the ultrasound to obtain the diagnostic information. Okay, how the ultrasound produces the image. This is 6 months. Okay, you have to remember. The use of ultrasound detected, reflected at the boundaries, reflected 1 mark. Received and detected by the transducer of process and display occurring in deep formation. Between the transmission and receipt path deep formation. The depth of the boundary, the time tells the time between the transmission, the time between the transmission tells the depth of the boundary, 1 mark. The intensity of the reflected beam tells the nature of the boundary. The last 2 points need to be included. Okay. The time tells the depth of the boundary. The intensity of the reflected beam tells the nature of the boundary. Okay. Made of what type of tissue? So, qualitative question ultrasound, easy. Just remember this point. Yeah. They can ask about it. Yeah. Difficult one, of course, the calculation. There's only one rigid one, just now I told you. Yeah. Okay, let's go more calculation question. Okay, this is another one. Give a try. Okay. Can't see, you see that. Yeah. Okay, so yeah, acoustic impedance for muscle bone given, absorption coefficient given, and the picture 4.1 centimeter of muscle, ultrasound gets into the muscle bone area. So reflection coefficient formula given for you to use. The attenuation of ultra muscle follows similar relation of attenuation Xray effect. Okay. The parallel beam of ultrasound intensity I enters the surface of the muscle, thickness of 4.1 centimeter. The ultrasound is reflected at the muscle bone boundary, it tends to the surface of the muscle. See, so right, the muscle reflected from the bone go up to the surface of the muscle. Calculate the intensity of reflection of coefficient of the muscle bone. The 2 part by part. Okay, first one, how do you want to answer? Calculate. Find the intensity reflection coefficient. Alpha, how much? For the muscle bone boundary. Come on. Okay, calculate, come on. And the intensity reflection coefficient, alpha, right? Alpha is IR over I. So what's the formula? Z2 minus Z1 squared over Z2 plus Z1 squared. Okay, so that's it. Then follow, once you got the answer, go to the second one. The fraction of incident intensity that is transmitted to the surface of the muscle and the surface of the bone. It is only one absorption. The second one only one absorption, right? From muscle to bone, right? Only absorption. What is the fraction of incident intensity that is transmitted from the surface of the muscle to the surface of the bone? Actually, the second one is E negative Kx, right? Second one just E negative Kx. So I equals to I naught E negative Kx, right? Only absorption for the second one. From muscle to bone, just going here, what is the fraction of intensity reached the bone? To just E negative Kx one, X 4.1 here, K trap, this is centimeter, this was in meter. Change, same unit. From meter have to change per centimeter. Or you change the centimeter to meter, anyone. It's 4.1 change meter, also can. Okay, so you got the answer. Let's recheck. The next slide is the answer. The answer is 1, 2, 3. So we go to the answer. Huh? So you get these answers. Yes, 0.05. Okay, the K, sometimes they use K, sometimes they use mu. Okay, both acceptable. Okay, but looks like more they use mu. Okay, they use mu. So I equals to I naught E negative Kx, right? Preferably go for mu. Okay, you write K also is not wrong, but negative mu x. Mu is the what? Mu is the absorption coefficient. Absorption coefficient. Don't mix up. Absorption coefficient, reflection, acoustic impedance, reflection coefficient. Okay, so first level. So I hope you got the answers. Okay, so we go to the next slide. So state what is meant by acoustic impedance or product of what is product of density times the sound. Explain why the acoustic impedance is important when the consider reflection of ultrasound and the boundary between the two media. Acoustic impedance determines how much of light they reflect, and different acoustic impedance determines the fraction of intensity that is reflected. That's why acoustic impedance is important. I explained the principle behind the ultrasound, the same idea we learned earlier. So a pulse of ultrasound produced by the transducer, every boundary partially reflected, partially transmitted. The time tells the depth of the boundary, the strength tells the nature of the boundary. Okay? So memorize that is very 6 marks. Okay, we go to calculation. The one calculation. So fat and muscle. So that's now bone, muscle, and bone. This fat and muscle, incident ultrasound, thickness is X. So acoustic impedance given, absorption given. Go to the question. The intensity of parallel ultrasound beam entering the surface H of the layer of fat is I. The beam is reflected from the boundary between the fat and muscle. The intensity reflected ultrasound detected at S at the fat is 0.012 I. Can you draw the diagram? From where to where? Where is I? Where is 0.012 I? The intensity reflection coefficient of the boundary between the fat and the muscle. The thickness X of here the other way around. They are asking for the thickness. Normally they ask for the fraction between the final and the initial intensity. But this one is they are asking for thickness. Final and initial intensity was provided. Working also here. Don't look at the work. Your time. So I think one is fine. Look at that two. Did it make sense for you? Okay. Okay, so yeah, so original attenuation is after 2 times absorption, right? 2 times absorption, 1 reflection. 0.012, original is 0.018. So 2 times, 0.018 is your 0.018 is your alpha. 0.012 is I over I naught. 0.012, yeah, 0.012 is the fraction of the incident intensity, final intensity to the incident intensity. 0.01, right? This is alpha, this is your E. So alpha 0.018, E 2 times the thickness, 2 times of the 2x, yeah, 2x. 2x times K. K is how much? K, which K? K of the fat, right? Yeah, K of the fat. K of the fat, or the mu of the fat is 48. Yeah, 48. So 48 year per meter. So here they put 48 times 10 power -2. So they change to centimeter or the K. So final answer you get in centimeter. Okay. You don't want to put -2 also can. So your final answer you get in meter. Okay. But 2x because 2 times, right? So E -2kx times alpha. Always for going down, absorb, reflect, absorb back. Okay. The ratio of the initial intensity to the final intensity. Okay. Okay, so yeah, that's the last one. So acoustic impedance is the product of density of the medium times the speed of sound in that medium. So again, medium speed, acoustic impedance here. Use delta to calculate the value for the density of bone. Oh, we want density of bone. Just use delta to find density of bone. No problem, right? So acoustic impedance is speed times the density, right? You can find the density here. Okay. If I check the unit, any problem with the unit, all aside. Okay, good. So the density is kg per meter cube. Oh, okay. So this is slightly different. Give it a try. 1 minute. Okay, so first answer is what? Answer yes, right? I equals to I theta. Okay. Second one, use the data to determine the reflection coefficient alpha and boundary between gel and soft tissue. The gel soft tissue just use the set of gel and soft tissue and find the alpha. Okay. The Z for both gel and soft tissue is given here, right? So yeah, gel and soft tissue. So you know the acoustic impedance. So input, so you get the. So it's straightforward. Straightforward. Gel soft tissue as soft tissue. Yeah. Yeah, I think the last part question is missing. From the answer, you know what is the question. So alpha 0.001 means majority reflected. When you use gel, 1. So why you need to use gel? So the majority of the incident in ultrasound to transmit to the skin. Okay. This is the proof. Okay. And with the skin, 0.001. Only 0.1%. We call. Sorry, this is with the gel, right? This is with the gel. This is with the air and skin. We check. Yeah, this is air with soft tissue. Air with soft tissue, majority reflected. Alpha looks close to 1. Gel with soft tissue, the alpha found to be very small, close to 0. So majority transmitted. Okay. So what is what revealed? What is revealed from here? So very little transmission of air skin boundary. Complete transmission with gel skin boundary. When wave travel into out of the body, no gel, majority reflected. Gel, little reflected. That's the conclusion. So no gel means majority will be reflected, but gel means only little reflected. So gel needs to be used on the surface between the transducer and the skin. Okay, so that's all. Okay, ultrasound. So summary, just remember the 6 points. Just remember the 6 points. Okay, how it forms. Okay, just remember the 6 points. Summarize it, and the calculation. So calculation is not tricky one. Rigid, they cannot change it. Okay. Yeah. Okay, so want to take a break. Take a 5 minutes break. The class is 12 o'clock. So we have half an hour. So take a 5 minutes break. Can I start Xray? A bit more break. 10 minutes. 10 minutes break. Okay. So take a 10 minutes break. Take a 10 minutes break. Then you start at just 10 minutes of Xray line introduction. Just introduction. I stop at 11. Okay, I think you take 5 minutes break, just 10 minutes, I stop at 11:45. Okay, right? 10 minutes, just 10 minutes of introduction. Okay. Take 5 minutes break, yeah?
I used to watch a lot. Yeah, I watched a bit of that. When I did I can't stand manual. Dramas I used to watch I'm not standing up to watch drama. So every episode is like 40 minutes. Yeah, I mean, American and I just watched politics of the weekend, and then
Yeah, so just 5 or 7 minutes. Okay, so I will stop at 11:45. Just 5 to 6 minutes. Okay, X-ray. Okay, you know what is X-ray? X-ray. X. Very fun. No Chinese name, right? Just X-ray, like X5. X-ray shows that it was found coincidentally. X-ray is a ray that found coincidentally. Okay, and they conduct the electron gun. Okay, and the electron go and collide with the metal surface, give up some sort of radiation. Unknown radiation. Lucky that when he conduct the experiment, the scientist, he got a photographic plate nearby in this lab, and the photographic plate changed color. And only get to know that there is an invisible ray was forming. Okay. Later found to be very useful. Yeah, so all the technique we call remote sensing, known from so X-ray, MRI, ultrasound. We won't talk about MRI, removed from the syllabus fluid. Replaced with PET scan. So used to check any damage to the bone. Okay. How X-ray is produced? This is the machine produces X-ray. Okay. So how X-ray produced? This is how it's produced. X-ray is produced when a high-speed electron bombarded to a metal surface. High-speed electron from a filament tungsten. Electron was released. The electron was accelerated to the anode. The electron was collided with the anode. The kinetic energy of the electron changed to 99%, changed to 90, more than 90%, changed to heat energy, less than 10%. Most of the books say it's 1%, changed to X-ray. Okay. So the efficiency of the X-ray tube, how much? Less than 10%. Most of the time it's like 1% efficient. Okay. 1% change to X-ray. Okay. So you got the X-ray comes up. Okay, X-ray produces. The produce of X-ray, to produce X-ray, the electron need to be accelerated with by using a voltage of 20 to 100 kilovolt. Okay. It's actually electron gun, how you found in CRO. CRO, same electron go and hit the screen. Okay. But the speed of electron hit the screen on CRO is quite small. This one is quite, it's a very high voltage, 20 kilovolt. So the electron gives very high kinetic energy. When it collides, it decelerates and releases EM radiation, which is in form of X-ray region. X-ray comes up. Okay. So 2 marks. How X-ray produced? When a high-speed electron bombarded to a metal surface, the kinetic energy of the electron converted to X-ray. Okay. So that's why old TVs, the one who will not flat screen, the old one. Actually, the electron is the one hitting the screen. Okay. You don't go and watch close to the screen. What's the problem in case? Because the electron accelerates, hit the screen, it decelerates, so it gives up a small X-ray, okay, a weak X-ray produced. So my damage right. Okay. So yeah, so introduction to X-ray. How X-ray is produced. Okay. High-speed electron bombarded to a metal surface. The kinetic energy of the electron is converted to X-ray. How many percent? Less than 10%. Converted to X-ray. 20 kilovolt may be used for your checking your bone. 100 kilovolt used maybe to kill cancer cells. Cancer cells also they use X-ray to kill. Yeah, maybe they use 100 kilovolt to kill the cancer cells. Okay, and the X-ray comes out from the tube. The intensity of X-ray versus wavelength it produces was like this. Yeah. So this could be a 7 marks question. It asks you to explain why the graph like this. Why the X-ray comes out from the tube is showing this type of shape. The 3 reasons they want you to explain is why the X-ray comes out from the tube. The X-ray comes out as a range of wavelength. Why does a range of wavelength? The X-ray comes out as a range of wavelength. Why the X-ray comes out as a certain minimum wavelength? Why cut off? Why not up to 0? Why there is a cutoff? And third, the weird one, why certain wavelength has a very high intensity, the spike, right, as a spike. Okay, so this is a 7-mark question. They will ask you to explain. Okay, so for this explanation, this is called Bremsstrahlung, German meaning breaking the radiation. So first you need to understand why first of all the electron produces X-ray. Okay, recall back what Maxwell said. I introduced in quantum physics. I said Maxwell found what when a charged particle accelerates and slows down, and there is an acceleration, accelerate or decelerate. Okay, give up EM radiation. Okay, since an high-speed electron strikes a metal target, a large acceleration occurs. The radiation produced in X-ray region. Since the electron has a continuous distribution acceleration, you see here, when the electron go and get into the metal, every atom is like a planet, the electron like a small spaceship going in. So you're going to collide few atoms and finally stops. Okay? Let's say it make 5 collisions before it stops. Okay? That means it has 5 different types of acceleration. Okay? Every acceleration will give out X-ray. Okay? So the how high is the frequency of the X-ray depend to how big is the acceleration. Okay? The acceleration is quite big. When you collide the deceleration like it's quite big. The X-ray will have a big frequency. Okay? Big frequency. So since the electron have a continuous distribution of acceleration, means what? Because it makes a range of collision, therefore it has a range of distribution of acceleration. Okay? You don't accelerate once, it accelerates maybe 5 times before it stops. Okay? So 5 different acceleration leads to 5 different X-ray frequency. So different X-ray frequency means different wavelength produced. Okay? So continuous distribution of wavelength is produced. Okay? So this is reason for what? Why the X-ray has a range of wavelength. Okay? Why the X-ray has a range of wavelength? Because electron make a series of collision. Therefore, the electron has a range, as a distribution of acceleration. Therefore, a range of wavelength is produced. Okay? Range of wavelength is produced. So 3 mark. Okay? The last example. Yes, that's why it's in a range. Okay? Why there is a cutoff? Cutoff happens when the electron, there is one electron going collide with the head-on collision. Not all, one electron might, unfortunately, go to the atom, it goes head-on collision. That means the electron make only one collision, stops immediately. That means all its energy converted to one single photon. Just change to one single photon. Okay? That means greatest acceleration happens. So all the energy of the electron will convert to one single photon. What is the energy possessed by the electron? How much energy possessed by the electron? First of all, how electron got energy from the electron gun? Okay. Do you remember the kinetic energy gained by the electron is EV, the voltage applied in the electron gun times the charge, right? So this is the energy possessed by the electron, EV. All the electron kinetic energy converted to one photon. Photon formula is what? Hc over lambda. So this is the smallest wavelength produced. Smallest wavelength happens due to what? The electron make a metal collision. Few million electrons get into the target. Not all going to make a series of collisions. Some make 5 collisions, some makes 10 collisions. The one make 10 collisions give 10 wavelength. The one make 5 collisions give 5. The one head on give only one photon, shortest wavelength. Okay, that's why you have a cutoff. Okay, there is a certain wavelength. Cutoff wavelength. Okay. So in exam they'll ask you to find how much is wavelength, cutoff wavelength. So the formula you must use EV equals to Hc over lambda. All the kinetic energy of the electron convert to one photon. Okay. So that's all. I stop here. Only this. Okay. Remember why it's the range of wavelength. Why the cutoff happens. Okay. That's the next class. Cutoff by T. Okay. Why is 5.
What is the range of wavelength?
Why a range of wavelength happens? Because first of all, why radiation happens for the electron? Because electron experience a series of acceleration. It slows down, it slows down. There is acceleration. Acceleration is actually deceleration, like deceleration. So when it slows down, the energy convert to EM radiation. Okay, that's the first point. First point is how electron produces EM radiation. When a charged particle accelerates, you give up EM radiation. That's the point of Maxwell. Okay. So here electron makes a series of collision. Therefore, it makes a series of acceleration. Therefore, a range of wavelength is produced. Okay. So that's why wavelength is in a range. Let's think about it. Next class tomorrow we continue. Take a short break before your chemistry. Okay. Minimum wavelength happens when the electron make head-on collision. Let's say the electron got 10 EV electron. You make 5 collision, finally it stops. The 10 EV energy convert to 5 photon. Each photon got energy, a fraction of 10 EV energy. Maybe the first one got 3 EV, second one is 2 EV, like that. But if that 10 EV go and collide head-on, all the 10 EV convert to 1 photon. All the 10 EV go collide, it stops, That means all the energy convert to 1 photon only. Collide with the metal, the anode. Collide with the atom of the metal. So you see the setting here. The electron go and collide with the anode. It's a metal. So you collide with the atom of the metal. When you collide with the atom of the metal, the electron stops. The electron which accelerates will stop. Then you hit the metal. When it stops, the kinetic energy of the electron convert to Xray. Change to Xray. Okay. So the electron incoming, some make 10 collisions, some make 5 collisions, depend. If the one make 8-on collision, you only give up 1 photon. That 1 photon got lots of energy. Okay. Lots of energy means short wavelength. The shortest bit.
So why is it called minimum energy?
Minimum wavelength. Cannot be minimum energy. Is it minimum energy?
Oh yeah.
It's a minimum wavelength. Okay, class, so we continue next class. Okay, stop. Thanks. See you now.